Step into the world of power, loyalty, and luck.
I'm gonna make him an offer he can't refuse.
With family, cannolis, and spins mean everything.
Now, you wanna get mixed up in the family business.
Introducing The Godfather at ChumbaCasino.com. Test your luck in the shadowy world of The Godfather slot.
Someday, I will call upon you to do a service for me.
Play The Godfather now at ChumbaCasino.com.
Welcome to the family.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.
Hi there. Welcome to The Logic of Risk, episode 15. It's great to see so many of you still following along. Thank you for your ongoing support. If you enjoy this podcast, please share it with others. And feel free to contact me if you have any questions, comments, or ideas for future episodes. Let's start. If you recall, in the last two episodes we introduced some technical terminology and a bit of formalism. We talked about measurable spaces and probabilities, and then moved on to random variables. I hope the discussion has been sufficiently clear, and once again I ask you not to give up if something isn't clear. In fact, please let me know. Please also note that on thelogicofrisk.com you can find additional materials, including full transcripts of my speeches, to ensure clarity in case the audio quality or my pronunciation isn't perfect. If you are new here, a word of advice. Please listen to everything discussed so far. We will need all these concepts. For pedagogical reasons, I tend to repeat myself, but I cannot dedicate the same amount of time to each concept every time. Speaking of random variables, we mentioned that these are quantities that can take on different values with given probabilities in correspondence with different random events. We use them to describe randomness in a more flexible and mathematically manageable way. One of the tools used to describe how a random variable assumes various possible values and the probability with which it takes each value is called the cumulative distribution function, CDF, or cumulative probability function. It is usually denoted by the capital letter F. Please note that capital F should not be confused with the cursive or calligraphic capital F, which we use to represent the sigma algebra corresponding to the event space. Given a random variable capital X, its cumulative distribution function capital F, evaluated at lowercase x, tells us the probability that capital X is less than or equal to small x. Remember that in probability theory, uppercase letters denote random objects, such as random variables or probability measures, while lowercase letters denote specific values. Thus, while capital X represents the random variable, small x is simply a placeholder for a particular value, say 4. The value of capital F evaluated at small x equal to 4 tells us the probability that capital X is less than or equal to 4. Clearly, capital F depends closely on our probability measure capital P, defined on the probability space omega, calligraphic F, capital P, where omega is the sample space and the calligraphic F is the sigma algebra of events. To spare you further repetition, I will stop specifying uppercase versus lowercase unless necessary. For any doubts, feel free to check the scripts. The cumulative distribution function f is defined on a set of values the random variable can take. This set is called the support of the distribution. Let's take an example. Assume that a given investment can generate only 3 outcomes. I deliberately choose small, easy-to-handle numbers. we denote the profits and losses of the investment by the random variable x. Based on historical data, or because someone we trust told us, or even by divine revelation, we know that we can expect a profit of 2 euros with a 40% probability, a zero profit, that is 0, with a 10% probability, and a loss of 1 euro, that is -1, with a 50% probability. Thus, ordered from smallest to largest, the values -1, the loss, 0 and 2 represent the support of the random variable x and serve as the reference points for its cumulative distribution function. This function is calculated as follows. In our problem, what is the probability of observing a loss greater than 1 euro in absolute terms? It is clearly 0, since we know that at most we lose 1 euro with a 50% probability. Therefore, our cumulative distribution function f will be 0 for every value less than -1. For instance, -3.5 would represent a loss of 3.5 euros, but in our example that outcome is impossible, so its probability is 0. And what is the probability of losing exactly 1 euro? It is 50%, so our cumulative distribution function jumps from 0 to 0.5 at the point -1. In other words, the probability of observing a value less than or equal to -1 is 0.5. We assign a 0 probability to values lower than -1 and add 0.5 at -1. What is the probability of observing a value less than or equal to 0? Well, we can observe -1 with a probability of 50% and 0 with a probability of 10%, so our CDF at 0 jumps from 0.5 to 0.6. This is because we are accumulating the probabilities, which is why the CDF is also called the cumulative probability function. So, what is the probability of observing a value less than or equal to 1? It remains 0.6 or 60%. In other words, we can observe -1 and 0, but not 1. We must wait for the value 2 for another jump in f. The probability of observing any value strictly less than 2 remains fixed at 0.6, and then only at 2 does it jump to 1. In fact, we have 0.6 plus 0.4, the probability of observing 2. For values greater than 2, our cumulative function cannot increase further and will remain at 1, since values above 2 are not possible in our simple example. Once the value 2 is reached, we have encountered a certain event. That is, one of the possible outcomes, -1, 0, or 2, has occurred, and the probability reaches 1 and cannot go any higher. Based on what we have just seen, we can already note some important points. The cumulative distribution function, the CDF, accumulates the probabilities associated with the random variable x. Hence, it represents the probability that a random observation is less than or equal to the specific value where we evaluate f. Being a cumulative probability, the more outcomes we consider once we have sorted them from smallest to largest, the higher the cumulative probability becomes. F will always be 0 to the left of the smallest outcome, which can, as in our example, be a negative number, and will always be 1 to the right of the largest outcome. These extreme outcomes are called the endpoints of the support, the left endpoint and the right endpoint. In our example, these endpoints are finite values, -1 and 2. But sometimes, at the modeling level, we might assume the support to extend to minus and plus infinity. In that case, we say that the limit of f is 0 for values of x tending to minus infinity, and 1 for values tending to plus infinity. As we move from the smallest outcome to the largest, the cumulative distribution function either remains constant or increases, but it cannot decrease. It takes values between 0 and 1. In fact, it is a non-decreasing function that represents cumulative probability. In our example, it was 0.5 for values less than or equal to minus 1, jumped to 0.6 at 0, and remained constant at 0.5 between minus 1 and 0. Once again, on thelogicofrisk.com, you can find a graphical summary of what has been discussed so far. A cumulative distribution function, a CDF, can be derived as we did, and as you can clearly see in the picture on my website, by ordering the outcomes and manually accumulating the probabilities. Whether there are 3 outcomes or 20, it is not a big problem. It may be tedious, of course, but it is entirely manageable. However, for modeling purposes, it is often useful to express f as a genuine mathematical function. For example, I could define f for my random variable x as follows: f of x equal to 0 for values of x less than 0, and f of x equal to 1 minus e to the minus lambda x for non-negative x, with e denoting Euler's number, and lambda a positive parameter that, we shall see, is called intensity. This means that the random variable x is exponentially distributed, or, in short, x is an exponential. An exponential is an example of a continuous random variable, since it can take on any value, not just discrete ones, between 0 and plus infinity. It is widely used in statistics and has countless applications. We will encounter it again soon. Of course, we can also have discrete random variables, such as the one in the example we considered. Or we can think about the Bernoulli random variable from the last episode. Its cumulative distribution function is 0 for values of x strictly less than 0, equal to 1 minus p for values from 0 inclusive up to but not including 1, and 1 for values of 1 and above. From the cumulative distribution function, many pieces of information regarding a given random variable can be obtained. In fact, it characterizes the probabilistic behavior of the random variable we are studying to model risk. But this is something we will explore next time, so please hold on and be patient. You will soon see how all these technical concepts allow us to do some quite interesting things in practice. It is not just sterile blah blah blah, like when people blabber about artificial intelligence these days without any idea of what a basic linear regression is. You need strong foundations to build a sturdy and valuable house. And that's exactly what we are doing. We are laying the foundations, strong foundations. Galileo Galilei, one of the fathers of modern science, used to say that l'universo è scritto in lingua matematica, which translates into the universe is written in a mathematical language. It appears we have to learn at least a bit of this language in order to do something meaningful. Trust me, it is totally worth it. What we are learning together will turn out useful in your daily life. Just wait for it. Ciao ciao!
Step into the world of power, loyalty, and luck.
I'm gonna make him an offer he can't refuse.
With family, cannolis, and spins mean everything.
Now, you wanna get mixed up in the family business.
Introducing The Godfather at ChumbaCasino.com. Test your luck in the shadowy world of The Godfather slot.
Someday, I will call upon you to do a service for me.
Play The Godfather now at ChumbaCasino.com.
Welcome to the family.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.